All right, I wanted to take a little bit of time and just run through these problems that we did on Wednesday. Some of them were good, some of them need a little bit of touching up, and we had to finish a few problems because we didn't have time to finish them on Wednesday. So I'm just going to run through all the problems. The ones that we had good, I'll tell you these are good, and some of them we have to fix, some of them we got to finish up. So number 1A, this one was correct, f prime of 5, negative 5/3. That one was good. The next one, same thing here. We had our derivative. This derivative was correct. We did our product rule. This was all good. Negative 190 over 3. That one was also correct, so we can check that one off. This one was also, again, a little messy with our doing our quotient rule, low d high minus high d low over low squared. We got that one. That one was all good. Negative 62 over 121. That did not simplify. I would just leave it like that. That one's good. So that one was good. So we can check that one off. That one was good. Same thing here with this one. This one was good using our second fundamental theorem of calculus. One thing that you do have to remember is when we cleaned up m of x, when you plug this 2x in here, it's not just g of 2x. You have to take the derivative of the inside. That's what that d of t or dt means, which we talked about that. So we had that part, and then we did our derivative, which again involved chain rule. So 4g prime of when we plug 2.5 in here, 2 times 2.5 give us 5. This one was correct. We got that one right. So that one was good. This is where it started to come apart a little bit. So I had this one started off correctly. So one thing that I want to do is I was on the right track here, but what I missed was just incorporating that first part. So this was, excuse me, this is what we were trying to find here was the m prime of some c value, you know, just using the mean value theorem. So this was m prime of c using the mean value theorem. This is what we do. So I had it started off right, but what I forgot was incorporating, and this is where I was messed up, was I was looking for numbers for these, and that's not what we needed to do. So this is where I was missing that extra piece. So this is where I'll pick it up here, and I'll finish this one off. So what we're looking for here is m prime of 2.5, all right? Well, that's what we just did in that last problem, okay? That's what we just did there. That was negative 20 over 3, okay? We just did that in this problem right here, negative 20 over 3. And again, that was the piece I was missing in addition to this extra piece over here. So this is equal to m of 4 minus m of 1. So m of 4, okay, if we plug, let me just erase this here. Let me switch this up. I'm gonna kind of block this off right here. If we come back over here to this part right here, we have a formula for m. So I'm gonna steal this formula right here because this is the other part that I was missing also. I just wasn't really thinking about it. So m of x is equal to that 2 times g of 2x. All right, so when I use m of 4, I'm going to plug that in there. So that's going to be 2 times g of, and then 2 times 4 is going to give me 8, which I'll do in the next step. And then minus m of 1, so again, that's going to be 2 times g of 2 times 1. Which again, like I was saying, when we use this 1 and 4 here, when we plug that in, you know, g of 2 times 4 is 8 and 2 times 1 is 2, so that's where that comes into play, but I was just missing out on that. And this is over 4 minus 1 that we have right here. This 4 minus 1 is 3. Okay, now when we do this, when we finish this problem out, if we have a fraction here, first of all, the denominators are both 3, so if the denominators are equal, then that means the numerators have to be equal. So negative 20, I'm going to clean up the numerator here now, so 2g of 8 minus 2, minus 2g of 2. All right, so we're almost there, and this is the other part that I was missing. We're looking for, come back up to the problem, we're looking for g of 8 minus g of 2. So all we have to do now is just take this whole problem and divide everything by 2 to get rid of all this. So negative 10 is equal to g of 8 minus g of 2, which is what we're looking for, that g of 8 minus g of 2. So the answer here is negative 10. That's what we were trying to get, g of 8 minus g of 2. And again, the part that I was missing, what I just wasn't thinking about, was I was looking for numbers for g of 8 and g of 2. And that's not what we were trying to get. We were just trying to get that expression, g of 8 minus g of 2. We were just trying to get this expression here and just show what it was equal to, and that's what we ended up with there, that negative 10. But just to kind of emphasize like what I was talking about the other day, try to pick up as many points as you can. So, you know, me showing this part right here with this mean value theorem, you know, you just want to try and pick up some points. So showing the mean value theorem might get you a point. It might not, I don't know, but if it gets you 1 point, that's better than leaving it blank and getting no points. You know, if you leave it blank, you're not getting anything. So if you can get a point, pick up some points here and there, you know, that's better than nothing. All right, so that's what they were looking for there with that one that I wanted to finish up. All right, this one here, again, I did not completely read this. They were actually looking for numbers here for this one, and I just misread that. I saw L'Hopital's rule, and I just took the derivative and ran with it. So this one, I'm just going to completely erase this, and I'm going to start over with this one. When I went back through and reread it, we're looking to actually find some numbers for f of 5 and f prime of 5, where I kind of had some expressions for f of 5 and f prime of 5, and that was way off. So let me just come back through, and I'm just going to redo this problem here. Okay, so the first thing that we know here is that from the stem part, which I don't have here, we know that the limit as x approaches 5 of g of x is equal to, this is the same thing as plugging in g of 5, which is 1, right? We know that from the stem, from the very beginning of it. Okay, so we know that we can evaluate this using L'Hopital's rule. So we know that g of 5 is equal to 1 from the beginning part of the problem. Okay, so we know we can do the limit of this. We also know in the beginning, in that stem part, let me come back here, we know that g and h are twice differentiable functions. So we know that it's differentiable. We know that that means, that also implies, because it's differentiable, we know that it's continuous. Okay, so we know some pieces of information there. All right, so now we can actually go through and find some other pieces of information here. Okay, so let's first of all, let's go through and find f of 5. All right, so again, because this says using L'Hopital's rule, what that tells us is that if we take the limit of this, that means we would either be left with 0 over 0 or infinity over infinity. So if we look at the limit as x approaches 5 of, we can just look at these separately, kind of like what we did, but I jumped right into the derivative instead of, you know, looking at plugging these numbers in first. I just jumped right into the derivative, and I shouldn't have done that right away. Pi x or x pi, doesn't matter. So if I plug 5 in here, we know it's continuous, so we can plug 5 in. So this means that we're going to end up with, if we plug 5 in, we have 5 plus 5 cosine of, now if we plug 5 in here for x, 1/5 times 5 is just 1, so that's going to be cosine of pi. So cosine of pi, this right here, just gives us -1. So that means we're left with 5 minus 5, which is 0. Okay? So L'Hopital's rule means, like I said, you should have watched that video on L'Hopital's rule. That was something that we didn't get a chance to cover in class. So this means that we're going to have a 0 over 0 case. So that means the denominator has to be equal to 0. Okay, so now, since we know that, this means that the limit as x approaches 5 of the denominator, 3 minus square root of f of x. When we plug 5 in here, 3 minus square root of f of 5, oops, f of 5, there we go, has to equal 0. Again, L'Hopital's rule says if the numerator is 0, the denominator is 0. That's part of L'Hopital's rule. Or it's infinity over infinity, which, again, we didn't get infinity here, so it has to be 0 over 0. Okay, so now we're just going to solve this for f of 5, because this will give us our first part of f of 5, okay, right here that I'm underlining at the top. So 3 is equal to square root of f of 5. Square both sides, you get 9 for, oops, not the square root anymore because I squared both sides. So square both sides, 3 squared is 9, square the square root, so we get f of 5 is equal to 9. Okay, so again, like I said, when I did this, I just jumped right into taking the derivative, and that is not the case yet. That is what we actually are going to do in the second part when we find our f prime of 5. Okay, so that's what we're actually going to do here for the second part. Okay, so let me move this down here and get a couple extra slides here. All right, so I'm going to take this function up top here, okay, and I'm just going to start taking the derivative. Now, you're not going to do the derivative like quotient rule, the low d high, high d low. You just take the derivative of each separately. So we're going to take the derivative of the top, and this is what we had done yesterday or Wednesday or whatever day it was. So this should look kind of familiar to you, all right? So we're just going to do the derivative of these separately. So the derivative of the top is 1 minus 5 sine 1/5 pi x times the derivative of the inside is pi over 5. That's a times. That's times, not divided by. And also, I should be limit as x approaches 5. We're going to have to plug 5 in there. And the derivative of the denominator is negative 1 over 2 square root of f of x times the derivative of the inside is f prime of x. Okay, so now let me jump up here to this part because we know we're dealing with g of x. We know that this is equal to 1. So this is another thing I was missing on my notes from yesterday. I had the derivative and all that, but I didn't set it equal to 1. All right, we know that the limit as x approaches 5 of g of x, this is the same thing as g of 5, and we know that that's equal to 1. That's all part of the continuous stuff, definition of something being continuous. If something is continuous, we can just plug 5 in, so g of 5 is equal to 1, so we know the limit as x approaches 5 of g of x has to be 1 also. So, whoops, too far. So we know that this whole limit here, when we plug 5 in, it's going to be equal to 1. So I'm going to plug 5 in, set it equal to 1, and then solve for this f prime of x right here. All right, so let's start off first of all by plugging in, let's plug in 5. So first of all, 1 minus, now let's see what we get here. If I plug in 5 for x right here, I'm plugging in 5. All right, so that means I'm going to be left with 5 sine 1/5 times 5 is just 1, so that's just sine of pi, which is nice because that's just going to end up giving us a 0. All right, so the whole numerator is just going to end up being 1. Okay, so this is all over negative 1 over 2 square root of f of 5 times f prime of 5. All right, now this is all equal to 1 for that reason that I just said a little while ago. Okay. Again, anytime you need to pause and rewind and go back and see what happened, feel free to do that. So like I said, this right here is all equal to 0, so that's gone. So I am left with, first of all, f of 5, we know, we just did this up above, is 9. Square root of 9 is 3. So again, numerator, the whole numerator is 1. That's all over 1 over negative, well, the negative sign was out front, but that doesn't matter, times 3 times f prime of 5 equals 1. So I'm going to clean up that denominator. 1 over f prime of 5 over negative 6. Whole thing is equal to 1. Just kind of separate that right there so I can finish this out here without extending the page. Bring that up there. So this is going to give us, if we do the negative 6 over f prime of 5 is equal to 1, that gives us f prime of 5 is equal to negative 6. There's your final answer for that one. Okay, so again, I'm not sure what all I was doing yesterday, but I was not getting values for f of 5 and f prime of 5. So f of 5 is 9 and f prime of 5 is negative 6. So that's what you should get for part F of that problem. And then part G, as I told you yesterday, this was all based on the squeeze theorem. So a couple of things to point out here. If something is continuous at 5, if something is continuous, you need to ask yourself 2 questions. At 5, that means does k of 5 exist? And the other thing you need to know is, does the limit as x approaches 5 of k of x exist? And basically, are these two the same? Okay, so that's what we're gonna try and do here. One of them is just kind of with the inequalities, and one of them is with squeeze theorem. So, all right, so that's where we're going to begin. Now we know that k of x is between h and g right here, all right, in that inequality. So first of all, we're going to start off with h. We want to know when x is 5 is less than or equal to k of 5 is less than or equal to g of 5. Okay. Now we know information about h of 5 and g of 5. h of 5 is 1, and also g of 5 is 1. So if 1 is less than or equal to k of 5 is less than or equal to 1, that means that k of 5 has to be equal to 1. All right. So we just did that first part. We just showed that k of 5 exists, and we just showed that it is equal to 1. The second part that we have to do is, this is where we actually are involving the squeeze theorem. So the limit as x approaches 5 of, what's the left one? H of x. Let me switch this up because I don't want it to all run together. I'm rewriting the same thing. I'm just going to use red. The limit as x approaches 5 of h of x is less than or equal to the limit. Basically, just applying the limit to all 3 functions should show, we want to try and show the same thing, okay? And we're still trying to get to 1. The limit, whoa. Kind of freaked out there for a second. All right, so let me move that over there. All right, less than or equal to the limit as x approaches 5 of g of x. All right, now, again, because of that setup before, we know that h and g are both continuous, twice differentiable and whatever. So if they are differentiable and continuous, then that means that we can plug in 5 into both of them, and we also know that their limits are 1. So same thing. 1 is less than or equal to the limit as x approaches 5 of k of x is less than or equal to 1. So again, we just showed the same thing, and that means that the limit as x approaches 5 of k of x has to equal 1. Okay, if it's greater than or equal to 1 and it's less than or equal to 1, that means it has to be 1, and that's the squeeze theorem. So we just did that second part. We showed that the limit of k of x exists as x approaches 5, and we also showed that they are the same. Okay, so not only did we show that k of 5 exists, and the limit as x approaches 5 of k of x exists, but we did show that they are the same thing. Okay, so again, if you have to brush up on your squeeze theorem because it was like September, October, whatever that we talked about that, that's what you get for those. All right, now there was only one part, I believe, maybe two parts in this second one that we need to talk about. So let's just run through these here real quick. A was good. You just had to find the derivative of f. So you were given that function of f. We took the derivative and we got this negative pi minus 1. That one was good. B, same thing. We got that one correct. That was okay. You can leave your answer the way I had it boxed there. You can write negative 1/3 times this. You could write pi plus 1 all over 3. It doesn't really matter. This, once you get to your numerical answer, that is perfectly fine. You could also use a calculator if you wanted to. It doesn't matter. This is perfectly fine. But part B was correct also. Part C, this was correct. You had your integral, fundamental theorem of calculus. Just says that we're going to do the integral of g prime gets you to g. So g of x evaluated from negative 5 to 1. It says we're going to do g of negative 1 minus g of negative 5. So we go to our table. 1 minus 10 gives you negative 9. That one was good. This is the one that we needed to do a little bit of work on. So let me fix this one here. The 5 over n, what we didn't really need to actually, this is what I was missing here. We didn't have enough pieces to actually rewrite the entire integral. And this right here, when I was looking at this, I wasn't entirely sure what the h was there for. And that is because this is the function of h of x. And the reason why there's a problem there is because h of x is the graph. So there really isn't a function because you have multiple functions in here. These are all line segments. So that's where the problem was coming in when I was looking at that. I didn't pick up on that h there, and that was the issue there. But 5 over n, this was the piece I was forgetting when we go from a summation to an integral. 5 over n is equal to b minus a over n. Okay, b minus a over n. Okay, you remember your integral. This goes from a to b of your whatever your function is. So we know that this a is starting at negative 1. So when we look at this, we have b minus a is negative 1 over n. N just means how many rectangles, right? So what we're looking at is b plus 1 over n. Well, we know that the numerator is 5, right? From this right here, from this fraction right here, we know that the numerator is 5, so that means that b has to equal 4. All right, so what we're looking at, what they're actually asking us to do here, the first thing they want us to do is write the integral. So the integral goes from negative 1, the top number is 4. That's what we were struggling with trying to find yesterday. You're not actually writing any function in here because it's just that function h of x. Okay, and again, I missed that h yesterday when we were talking about this, and that's why you can't actually write a function because it's a graph. We don't actually have the function to work with there because it's multiple parts. So this is just asking us to find the area under that curve for h from negative 4 to 1. So we come up here. Here's negative 1. And then we got 0, 1, 2, 3, 4. So we need to find all of these areas. So the first thing I notice is, and hopefully you guys notice it too, this area here and this area here cancel each other out. Okay, this one is negative 1/4, and this one up here is a positive 1/4. So they're going to cancel, so I'm just going to ignore those. I'm just finding these two areas here. Okay, so this area right here, it's just a triangle. So you got 1/2 base times height. Well, the base is 1 and the height is 1. So my first area is 1/2 plus. Second area is underneath the x-axis, so I'm just going to go ahead and change that plus to a minus so I don't forget it. That's just going to be a minus. And then again, it's a triangle, so 1/2 base times height. So 1/2, the base is 1 and the height is 3, and you can switch those if you want, doesn't matter. Base is 1, height is 3, or the base is 3 and the height is 1, whatever, it doesn't make a difference. So 1/2 minus 3/2, which gives you -1. Okay, so again, going from a summation to an integral might be something else to look at. And again, they had said in their review that these problems were a little bit harder than the ones they went over on Monday. So that's just something else to think about there for these problems, that these were a little more challenging than the ones they went over on Monday and Tuesday. All right, E. This one was correct. They used intermediate value theorem as their explanation, which is a good explanation, but that's basically what we were talking about, okay? When you go from -4 to -3, the derivative of g, so g prime of x, goes from -1 to 4, so that means that g prime had to be 0 in there. Same thing here, when you go from -2 to -1, g prime of x goes from a positive to a negative, so it has to be 0 in there. So there is a minimum, there has to be at least 2 points where this is a horizontal tangent. It's got a horizontal tangent line where the derivative is 0. At least 2. There could be more, but we know that there's at least 2. Okay? Again, and a couple other things in here. G is twice differentiable. So since g is twice differentiable, that means that the derivative is continuous. And then since the derivative is continuous, that means the intermediate value theorem applies. So again, you just want to, when it says justify, you want to use some calculus terms in there. So I just wanted to throw those explanations out there. So again, hopefully that clears up some things with these problems that we weren't able to go over on Wednesday or whatever day it was we talked about this. So if you have any other questions, just let me know. Send me an email or a comment on Google Classroom, and I'll try to answer those as soon as I can.